Start. Okay, we're recording, we're rolling. It's just after 9 o'clock in the morning on Monday, November the 9th. And we're going to cover the Ethernet theory and operation and Ethernet switches theory and operation, this particular one. But first of all, I want to cover a little bit in our announcement section. Let me bring our announcements up here. Stop sharing this. Share the tab with the announcements. That should be it. Okay, so I put it, oh, that's kind of dim looking. I put a new link here on the top. If I wiggle my mouse around here, it goes on the top here. And let me see if I go to, let's see, I think I'm on that tab. If I click on that, it should open it. Okay, the document there at the very top of the announcement is a new document that is recently posted, and it has the 2 links you need for this Texas Post-Secondary Career Fair for Cisco. If I roll all the way down to the bottom, Cisco Talent Bridge Career Prep Course, click on that one and enroll. That'll enroll you in the Cisco Networking Academy onto the Talent Bridge section. And then when the day of I'll go back to the very top of the document. I'll go down to just the first page, second page rather. This is the link that you click. The Cisco WebEx link is the link that you click to go into the meeting. It should be on November the 12th. This is this Thursday. We'll start at 2 o'clock. And you can click on this link now, and it'll let you save a little bit of time beforehand. You can put your email address and stuff in there. And then when you click on it Thursday and actually go into it, it won't take you quite as long to get in there. So I wanted to show that to you, and let me see now. Can I click again on the main announcements and bring them back up again? Okay, so this first link is what I just covered, this very top link. Click on the blue link, and that'll bring up that PDF file with those 2 links in there. The top link will, when you go the day of the career fair, and the bottom link, you can pre-register for this. So this second one here is just sort of a recap of that, the same link. Now, what course should I take this spring to continue toward getting the CCNA certification? And there's a bit of confusion here because Cisco revamped these certifications a little over a year ago, and here in education we haven't quite lined up all our course numbers yet. So don't take CCNA 2. If you take CCNA 2 in the spring, you're going to get this course all over again, what we used to call CCNA 1. Because CCNA 1 is turned into the new baby course. CCNA 2 is going to be this Introduction to Networks course that we're taking here at South Campus. And then 3 and 4 will be the final 2 courses. So once you complete this course here in the fall, the only courses you need to take in the spring is CCNA 3, which is the one I have in gray here, in the first 8 weeks, and then take the CCNA course in the last 8 weeks of the semester. And then so about the first week of May, you'll be completely prepared. You'll have every objective, every topic that's on the CCNA test, and you can go and attempt that exam. Okay, so let's see. Stop sharing this. Go back to this. Looks like we're still taping. Okay, good. So I'm going to start into the PowerPoint presentation show. Quite a few slides today, so gotta get started covering the stuff we need to cover. So we're going to look at how the theory and operation of how Ethernet works. We're going to look at this Ethernet MAC address thing. The address resolution protocol is the thing that lines up your layer 2 MAC address with your layer 3 IP address. We'll see how that works. And then we'll look at how Ethernet switches work. Ethernet switches work. Now we use a little fixed configuration switch in the lab, the 2960 switch, to make some bigger switches. We'll look at briefly at some of those things. Okay, so here we go. So Ethernet, when we look at this dreaded, feared, and hated OSI 7-layer reference model, you see Ethernet sits at the bottom 2 layers. It has a physical layer component because Ethernet translates bits from the computer into squiggles of electricity representing 1s and 0s, the physical bits that travel at the physical layer. And at the physical layer, we have 3 things. We have what kind of a bit is a 0, what kind of a bit is a 1, in the forms of what kind of electricity that is. We have a certain rate of speed, and then we have put the same kind of plugs and jacks at both ends of the wires so that we can successfully transmit these electrical bits, these ones and zeros. Or maybe it might be flashes of light through a fiber optic cable, or it might be radio frequency energy with Wi-Fi. So many different speeds are supported. So Ethernet is really split into two layers. And when you buy an Ethernet card at Fry's, you get two things. You get a physical printed circuit board, like a PCI card that could plug into the inside of your desktop PC. You might get a USB attached Ethernet card. And you'll also get in these boxes a device driver disk. This is the logical link control. This is the software that takes that physical hardware and interfaces it to your computer. Because you could be running Windows or Linux or Mac OS X or any number of other operating systems. And the driver disk shims that into your operating system that's running in the software in the upper layers of your PC. So if we look at this encapsulation and de-encapsulation thing, we talked about this in an earlier chapter. The PC that sends the data at the top, let's see, is it going to allow me to draw here? Okay, so this PC is sending some data, and he's going to have taken that hypertext transfer protocol information. He's going to have take that data, raw data at the application layer. He's going to put it in a TCP segment and put the TCP port numbers. And the TCP segment will be put in an IP packet with the IP information. And then the IP packet will be put in an Ethernet frame and actually transmitted through the bits of wires that were connected to there. Then after the information is transmitted out of the PC and it goes to, in this case, we have 3 routers between the source and the destination machine. The router is only interested in what's the, I need to look up, the router says, I need to look up the destination address and find that in my routing table so I can forward the packet properly. So it only opens it up to layer 3 and looks at that. He's not interested in the TCP port numbers or the application layer HTTP data. He's not a web browser. He just needs to look at that network information. So it passes through the 3 routers in turn, and eventually when it gets back to the ending workstation, he'll open up the packet. He'll open up the Ethernet frame. He'll pull out the packet. He'll open up the network packet at layer 3. He'll pull out the transport layer TCP segment. He'll open up the TCP segment, pull out the stream of data, the application data that corresponds to that hypertext transfer protocol data, and the data will appear on the screen. That's the concept of encapsulation and de-encapsulation. So network interface cards look like, well, here's one that's a PCI attached to the inside of a desktop PC. Over here we see a picture of it plugged into the backbone, the interface cards that are on the motherboard of the PC. On a laptop computer, it's likely going to be built right into the back of the computer. If it doesn't work, if it's failed, or it doesn't have one, you can buy the USB attached Ethernet adapter for a laptop to repair it without having to actually open up the laptop and repair it for $10. If you want to add an Ethernet adapter to a desktop PC, you don't feel like opening it up, you're not comfortable with doing the hardware stuff, just buy a USB attached one and plug it into the desktop machine, and you can have a second one, a replacement one. On our Cisco devices, the Ethernet ports are usually color-coded yellow, and there usually are 2 of them. So on the routers we use in the lab, we have 2 gigabit Ethernet ports. So the network interface adapter itself, in this case, they're showing the PCI attached, a card that would plug into a standard typical desktop computer. So it is, he says it's a layer 2 device. It's a data link layer device. Its sophistication rises to the data link layer because he has to speak at the, understand MAC addresses and send and receive bits from the network and so forth. So really, since he's actually talking over the physical link over the network, he's really a layer 1 and layer 2 device. So when we say something is a layer 2 device, like a NIC card is a layer 2 device, an Ethernet switch is a layer 2 device, it really has a lot of layer 1 functionality because it has to be able to communicate with the wires. But its sophistication rises to the level of layer 2. So for example, a router, which is a device that connects networks together, it's interested in the layer 3 information to look in this routing table and look up the best where to forward the packet. We call it a layer 3 device, even though it really has layer 2 and layer 1. It has layer 2, it understands Ethernet. It has layer 1 that understands bits. So common layer 2 network interface cards are Ethernet based. And the majority of communication in residential and commercial world today is Ethernet based. Token ring is a IBM technology that also uses MAC addresses, but it's not very common anymore. So Ethernet was 10 megabit, and then it's 100 megabit, gigabit or 1,000 megabit, and actually we have 100 gigabit Ethernet shipping today. It's gotten very, very fast. So let's trace this connection. We're going to take this card and we're going to plug it into our PC, and we're going to plug a connector onto the back of it. And we're going to take that connector and plug it into an Ethernet switch. So this Ethernet switch has got 7 PCs and a printer plugged into the ports of it. And the little yellow lines represent when one device needs to talk to another device. The switch will create a virtual circuit and connect the two together, much like the telephone company creates a virtual circuit when you call someone else's phone. So we'll take that PC and we'll plug it into, we'll take that Ethernet cable, we'll plug it into the Ethernet port on the back of the desktop PC, and we'll take the other end and plug it into somewhere near the PC at our place of business. There'll be a jack where we can plug it into the company network. From that wire in the back of your office, that wire goes back to a wiring closet at the TCC lab, our South Campus lab. That wiring closet is right outside the door we come in to go into the lab. And all those wires are connected to a patch panel on the left-hand side of your graphic. And on the right-hand side of your graphic, we use short patch panels to plug together all those individual people in those individual offices to a big Ethernet switch where they're all connected together. So patch panel connected to the switch ports, and everyone's connected. So our wiring closet looks like this, but it's 2 or 3 big racks full of switches in there because our building has got close to 1,000 different PCs that need to be connected. So the entire diagram here in this line drawing shows that the PC plugs into the wall. There's a wire that's been run behind the wall up in the ceiling that goes all the way to the patch panel in the closet. And then a technician has plugged the patch panel into the Ethernet switch. And the Ethernet switch itself is wired back to other Ethernet switches through our tunnel system that we have in our campus, fiber optic cables that connect all the buildings together. So Ethernet is best effort delivery. It's kind of like the mail system. You put something in the mail and it may or may not be delivered. Yeah, that mail-in voting ballot, it may or may not be delivered. We don't really know about that. So the postman just looks at the zip code as to tell it where to send it to. They don't really know or care what's inside the envelope itself. They have no way of checking. So if I take 2 Ethernet devices and plug them straight together, like we did in our last lab, we wired our 2 PCA PCB NIC cards together. But in the real world, we want more than just 2 people being able to talk to each other. So we plug everybody into Ethernet switches, and then all the Ethernet switches connect all the devices in our home or in our business or in our commercial environment where they can all talk to each other and share stuff on the Ethernet. So Ethernet is a protocol that allows information to be transmitted from one Ethernet NIC to another Ethernet NIC. It could be plugged into the same switch like this graphic is. It could be plugged into different Ethernet switches and routers in between them. So the logical link control portion of the Ethernet is that's that device driver disk that came when you bought a NIC card for $10. It came with a printed circuit board hardware that you plugged in, could be USB or PCI, and it came with a device driver that you could install the device driver for the Windows operating system. The Mac is the physical layer. That's the printed circuit board. It actually extends into the physical layer because it has the RJ45 connector and connects to the wire and makes transmission and reception of bits over the network possible. The LLC layer extends up into the software layers that are on that PC. They extend up into the operating system, typically the Windows operating system. So this data encapsulation process, we have maybe our bit of web data up here. And then when that was encapsulated into a TCP segment, and added the TCP header information like the port numbers. That TCP segment was encapsulated in an IP packet at layer 3. And then the IP packet itself was encapsulated in what's outlined in red here, the complete Ethernet frame. And the Ethernet frame, in turn, is turned into bits and shot out over the wire at the physical layer. So an Ethernet frame looks like this. We've got a preamble, and they're always the same for every Ethernet frame. This is just an alternating series of zeros and ones that allows synchronization between the devices. And then we have our first bit of unique information, which is what's the destination address of that device I'm trying to talk to. So this is 6 bytes. 6 bytes, there's 8 bits per byte, so that's where 6 times 8 is 48 bits. The destination Ethernet address is a MAC address, that's a 48-bit value. Then in the Ethernet frame will be the MAC address of the device that created this frame, his own source address. So that way the destination has somebody to answer. Then there's a type field which says what type of upper layer data is encapsulated in this Ethernet frame over here in the data portion. Is it a ping request? Is it an IP version 4 packet? Is it an IP version 6 packet? And the numeric value in the type field will tell us that. So for example, if it's 0800 hexadecimal, that means it's a regular old IP version 4 packet. When each Ethernet device transmits his frame, he takes all this data from here to here, the unique data, and he does a frame check sequence on them, a cyclic redundancy checksum, and he puts the 32-bit value in this frame check sequence field. The data will be transmitted along the wire, and if there's no errors when those bits are transmitted along the wire, the receiving workstation will recalculate the same exact sequence according to the bits that he received, and he should come up with the same exact 32-bit value. It's like a checksum or a frame check sequence. If the 32-bit values of what he heard on the wire match what he recalculated, he knows that the data is correct. It's okay. That can't be changed because if even one bit got changed at all, the numbers wouldn't match. So that's his error detection. It's not correction. Ethernet can detect an error, and if he detects the error and that the frame check sequence don't match anymore, he just drops. He drops the entire frame, and eventually some upper layer protocol will retransmit that when he doesn't get an acknowledgement back. So at the MAC sublayer, we've got this is the physically putting frames on the media, physically picking up frames on the media. It's communicating directly with the physical layer. It's actually sending and receiving the bits. Now, what happens if two devices try to transmit bits simultaneously? There could be a collision, and that because digital ones and zeros in binary, there's only zeros and ones. If we take the electricity for a 0 and a 1 and we add 2 ones together on the same time, oh no, we're going to get a collision. And so if I see in binary, there's only zeros and ones. If I see some binary 2s and 3s, that's not proper. There's no 2s and 3s in binary. So the electricity devices, the Ethernet devices can detect if a collision is occurring, and they have the method for recovering from collisions. This is called carrier sense multiple access collision detection. So Ethernet is kind of like the original Ethernet was like a party line in the country or extension phones in a house where if one person is using the phone and someone else picks up the extension, you could hear them. There's no privacy. There's no single connection that anybody's using. Hold on. Checking attendance. The heck, you're not going to let me do this? Okay, there we go. Sorry. So in Ethernet, anybody can transmit whenever they feel like it. I call it the Three Stooges poking their eyes out method. This is opportunistic. I can transmit whenever I feel like it. I can transmit. I'm supposed to listen to the wire first. So like if you have a party line at grandma's house in the country, and grandma wants to make a call, she picks up the phone, and if she doesn't hear a dial tone and she hears Farmer Jones talking, she knows she has to wait to make her call. She has to hang up and come back. So Ethernet is like this. An Ethernet device will listen to an Ethernet link, and if he hears any other bits, he will say, well, I can't transmit now. Someone else is transmitting. If I transmitted my ones and zeros now, that would form a collision, and it would ruin both of us, and we'd both have to start all over. So carrier sense means I can hear the other bits. Multiple access means many workstations can be connected to one single Ethernet link, like the old hubs to the old coaxial cables. And collision detection means, well, if two stations just happen to transmit at the same time, like we have here and here, their bits will add up to something other than 0 and 1, and everybody can easily figure out a collision is starting to occur. So our rules when a collision starts to occur is everybody stop immediately and wait a random interval of time and then try to retransmit. And whoever's random interval code chose to show this interval will get to retransmit again, and the second guy, when he tries to retransmit, he'll hear bits, he won't retransmit again, and there won't be another collision. So listen to the network to see if any other users are on the air. Are they trying to send something? I'm looking for no zeros and ones. So if that's true, I don't have to ask permission. No hub needs to grant me permission. I can transmit. I'm authorized to transmit whenever I don't hear other traffic. Now, if two PCs just happen to hear no traffic and just coincidentally try to transmit at the exact same instant, they will detect that the collision has occurred. So the PCs know this because they hear the collision. And when that occurs, the first PC sends out a gem signal, and then using a random backoff scheme, two PCs will start a random timer, and the PC that happened to get the luck of the draw this time and happened to randomly choose a lower timeout, backoff time, when he tries to retransmit again, the other one will still be waiting, and he'll be able to send his data. So we don't have to worry about collisions today much because we don't use hubs anymore. We use Ethernet switches. Ethernet switches have memory in them, and there's no collisions. So if you just have one Ethernet port of a switch running to one PC, they'll never have a collision. And this is what we do today because it gets better performance. We don't have to lose bandwidth due to collision. So full duplex Ethernet switches, there are no collisions. Why do they still use carrier sense multi-access collision detection in these switches? There's no collisions, right? Oh, well, what if I take one of these old 4-port hubs and plug them into my office and plug, say, my teacher machine and the student machine I'm setting up into the same hub, and that goes back to that one single Ethernet switch port in the closet? Well, now I could have collisions. So the switch still needs to be able to detect and recover from collisions. Now, Wi-Fi, that's a whole other thing. Wi-Fi transmissions is like a single shared radio channel. It's like the old Ethernet hubs. So Wi-Fi devices can create collisions. So Wi-Fi devices use an extra method to reduce the collisions called carrier sense multiple access collision avoidance, which means when a Wi-Fi laptop wants to transmit something, he sends out a little ping, I intend to transmit, everybody else be quiet. And then he sends his whole Ethernet frame over the Wi-Fi. So that further reduces the collisions in the Wi-Fi channels, which can be very congested. Let's look at this Ethernet identity question. All Ethernet devices have a hard-coded ROM burned into the read-only memory 48-bit value. The first half of this 24 bits is assigned by the IEEE. Anybody in the world that wants to make Ethernet devices can go to the IEEE and pay them a $1,500 fee, and they will assign them a unique 24-bit prefix called the Organizationally Unique Identifier, or OUI. And then once you have paid the $1,500 and get your OUI, you can start firing up, making printed circuit boards and making Ethernet NIC adapters, and you'll have your own organizational unique identifier, and you can make 2 to the power 24 of these devices, which is like 8 million. And then when you run out of 8 million, you can get another OUI. So some big companies like Dell and Cisco, well, they've made more than 8 million. So they've got several prefixes. And if you use a Wireshark sniffing program, Wireshark will look at these first 24 bits and figure out who manufactured that MAC address. So say Cisco or Dell when you look at the trace for Wireshark. And that's helpful to figure out if it's a workstation or a device. Every device with an Ethernet network interface card has a unique MAC address assigned. So anything that needs to plug and use the Ethernet. So this means that all our desktop client PC workstations, student machines, employee machines, all the servers, all the rack mount servers, all the printers, even switches and routers themselves have to have MAC addresses. They're sometimes called burned-in addresses because they're burned into a NIC card. They don't change. And they're written in 3 different methods. It can be written with dashes, with colons, or with periods. The Ethernet header of the Ethernet frame contains the source and destination MAC addresses. And each NIC card, whenever he hears an Ethernet frame, he will look to see if the destination and MAC address in that Ethernet frame that he just heard, you heard the bits on the wire, you put them together, he decoded the destination MAC address, and if it's his address, he needs to open up and de-encapsulate and send that up to the Windows operating system in that PC. If it doesn't match his own address, he stops processing the frame. There is one exception. If it's a broadcast frame, everybody has to process those. So when an Ethernet interface adapter hears this transmission, this guy is transmitted to this guy, and he's transmitted his source address, and he's transmitted the destination address. If the destination address matches his address, he knows that's being addressed to me, and he'll go ahead and decode the frame and send it up. So let's take a look here, and machine H1 has transmitted an Ethernet frame, and the source address is AAAAAA, and the destination address is CCC-SC-Cisco, and everybody's going to hear it. H2 hears it, H4 hears it, but they say, well, wait a minute, it's addressed to the C's. I'm all B's or I'm all D's. It's not addressed to me. I'm just going to ignore it. Workstation H3 says, that's me. That's my MAC address. I should open up this Ethernet frame and go ahead and send it to the upper software layers and let them process it. So that's how a bunch of Ethernet workstations can figure out whether they should process data or not. So Ethernet was originally Ethernet version 2. Ethernet version 1 was the prototype they used at the Palo Alto Research Center. So Ethernet version 2 is what we use today on the Ethernet. This is the one that survived. Everybody uses this version. There are some other versions here that I used to use back in the 90s with the Novell network stuff to get Macintoshes to work on Novell networks. So we don't have to worry about any of these types today. Okay, early versions of Ethernet were 10 megabit. And Ethernet 2, that one that was at the top of the last frame, that's what we still use today. Now, I'm going to call that a de facto standard because that's in fact what we use today. After Ethernet had been shipping on the market for several years and was very successful, being pushed by the big 3 companies that shipped them, Digital, Intel, and Xerox, DIX, the IEEE engineers said we need to have a committee and form a formal standard for Ethernet. That's what we know as the 802.3 standard. And because they're engineers, and because the only thing that 2 engineers will agree upon is that the 3rd engineer is wrong, they had to change the standard somewhat. So this is the standard they published, which nobody uses. It's an academic thing only. This is what we use today, the one that I have circled in blue on the bottom. So in 1979, at the Xerox Palo Alto Research Center in California, the Ethernet standard was developed originally as a method for sharing very expensive laser printers because laser printers were too expensive to buy one for every secretary that typed up documents. In 1980, the 3 big manufacturers got on board, Digital Equipment Corporation, DEC, Intel, and Xerox. They were the first ones to ship Ethernet product. In 1985, the IEEE guys got in and tried to muddy the waters, and everyone said, we're not paying attention to you whatsoever. Only in fundamentals of education, fundamentals of networking class are they even mentioned. So in 1985, we all got, originally Ethernet was a very thick coaxial cable. In 1985, we got a thin Ethernet standard. In 1990, the phone guys probably banged some sense into these guys' heads and said, why don't you use twisted pair cable? It's much easier than the coaxial cable. In 1995, fast Ethernet appeared on the scene. In 1997, we had the full duplex standard, and in 1998, you can tell this is an old chart, it ends in 1998, we got gigabit speed Ethernet. So the Ethernet size is not allowed to be any smaller than 64 bytes, because if it was less than 64 bytes, if a frame was formed that was less than 64 bytes, all the other devices would think some collision is occurring. This is not a valid frame. What if you only have 1 bit to transmit? See that green section here? I have to send a bit 1 that means yes, or a bit 0 that means no. And that's the only thing you need to send. Well, you need to pad out that payload section to make it at least 42 bytes in length. So that will keep the entire Ethernet frame from being less than 64 bytes long. You can put as many as 1,500 8-bit characters or bytes or octets into that payload section of the Ethernet frame. Any bigger than that, it's a giant, and it could cause a problem. Now, we haven't, oh, no fair, we haven't talked about VLANs yet. We'll talk about that in a second 8-week thing. VLANs are a way of dividing up switches that go to different departments so they don't have to hear each other's broadcasts and each other's traffic. So if we want to tag the frame with that VLAN identification number, we just simply are going to add this extra encapsulation to it. But we'll get that in a later course. Try not to worry about that now. So back to the standard Ethernet frame. We have our preamble and start of frame delivered to that first red square at the left side. That's that 64 bits of alternating zeros and ones. And then we have our destination address and our source address. And then the type field. IEEE said, let's call it a length field and use this for, Novell NetWare when he's doing Apple Macintoshes on the Novell network file and print sharing, which I did in the 90s. But no one uses that on the internet. No one hardly uses that anymore. So we're going to make the length field, the type field, and that's going to be that field that says, if I put 0800 in here, it's an IP version 4 packet. The frame check sequence is this theory I talked about earlier, that when the sending workstation sends the entire Ethernet frame, he calculates 32-bit CRC and appends it to the end of the frame where this red square is. And when the receiving workstation hears it, he recalculates it, and it should match. If any of the bits have been corrupted on the wire in their journey from source to destination, the bits will not match. And this will detect this, and the receiving workstation will say, I can't rely upon this Ethernet frame. It has become bogus, and I will instantly drop it. I will discard it. Now, this MAC address is expressed in hexadecimal. In the hexadecimal code, we have 16 numbered values. So we have 1 through 9, 0, 1 through 9, like we have in the decimal number system. We need some single digit to identify what in decimal is 10, 11, 12, 13, 14, and 15. We can't use 10 because 1, 0 in hexadecimal means 16. So we need to use the single digits. That's why you always see A, B, C's, D's, E's, and F's in hexadecimal numbers. And network administrators have learned over the years that we can spell some very amusing phrases with just A, B, C, D, E, and F, like dead beef or feed face, things of that nature. Name our networks with amusing characters with hexadecimal. So this is the number system that's used in hexadecimal numbers because they're so big. With 32-bit IP addresses, we use dotted decimal to represent the 32-bit binary value, because if you try to look at binary numbers, you just get a headache. For the 48-bit hexadecimal, with 48-bit MAC addresses, we use hexadecimal. We also use hexadecimal for the 128-bit IP version 6 values that we'll see later on. So we could see it with dashes, with colons, or with periods. Any one of these are valid. So if you go in your Windows workstation and type ipconfig all, you'll get it with the dashes. Depending on which device you're using, you might get a different representation, but notice that the numbers are the same. So in a MAC address for any Ethernet device is going to be the first half of the 24 bits represents the manufacturer that manufactured that device. And the last 24 bits, the manufacturer agrees to never make two that have the same value. It must be unique. If two NIC cards ended up in the same room with the same exact 48-bit value, it would break the network. So if you run out of your 24 bits, you need to come back and give the IEEE another $1,500 and make some more. So when you go into the Windows operating system, you type ipconfig, you can see the IP address. If you want to see the MAC address, you type ipconfig all, and you get the physical address. Okay, let's talk about methods of transmission. Unicast is one-to-one. This is like a private telephone call, and you're not on the party line. So on a unicast MAC address, I'm transmitting something straight to a specific, in this case, this user is trying to talk to the server, trying to log into the server. Kind of like when you come into the lab and you log on to your TCC identity to try to get and open up the workstation to use it. So the destination MAC address is going to be the MAC address of the server, ends in a 28, ends in a 28. And the source MAC address is going to be the physical MAC address of the source machine that created the traffic, ends in 53, ends in 53, same address. And then this violet colored part here is the upper layer encapsulated data, typically an IP packet. Now, what if I want to send a broadcast? What if there's some circumstances that I don't need to send to one other guy? I need to send to everybody. I have to call for help. There are two instances where we broadcast today in networks. The first is if I'm making an ARP request, no fair, we haven't talked about ARP yet. I need to find what your layer 2 MAC address is so you can send me back an answer to a ping, for example. Well, I'm going to broadcast out a request, and I'm going to set that destination MAC address to a special value of all Fs. That's a special number that no NIC really has. It's a code for a broadcast. The switch will do me a favor, and he will flood the broadcast out all his ports. All the devices will hear it. Only the device that can help me will respond. So if I'm making an ARP request, only the device that has that IP address will tell me what his MAC address is. The other common use for broadcast is the DHCP function that automatically assigns IP addresses. When you first flip on a machine, he'll send out a broadcast, DHCP broadcast. Please, Mr. Server, give me my IP address so I can start being on the network. Multicast is a special, not quite as noisy as broadcasts that are used. Routers use multicast to send routing tables to each other. Or if you're going to one of these streaming audio or video, if you're using YouTube or you're going to the CNN news update, which is being sent out to a million people at the same time, they multicast that stuff. They don't send out a million copies of it. They send out one copy of it and just tell everybody to listen to this particular multicast address. So it's a way of keeping reducing traffic on the network. Okay, now let's look at MAC addresses and IP addresses. As you put your mail into the mail system, first of all, it's physically encapsulated in your mailbox, and then the mailman takes it and he puts it in his leather bag, and then it goes to a mail sorting center, and then it goes to in a truck or a plane across the country, and then it goes to a delivery center, and then it gets put in that guy's mailbox. The address on the mail envelope doesn't change. This address doesn't ever change. No one scratches this out and writes codes like brown leather bag, plane, truck. They leave that there. The IP address of an IP packet is like a mail envelope. Its numbers don't change. But the MAC addresses that these packets get encapsulated into hop by hop as they go from one source machine to a destination machine are constantly changed with each hop. So MAC addresses change all the time. It's like different trucks. That will happen as it proceeds through the network. So a switch is a layer 2 device. A switch is a device that makes its forwarding decision based upon the destination MAC address. So when 24 students are plugged into the same room and one pings another workstation, they will give them connectivity to each other. So we call switches layer 2 devices. Routers are layer 3 devices. They connect networks together. And routers make their forwarding decision based upon the network address, not the MAC address. Because MAC addresses only survive in your local area network in your house or at your company. They don't go through the rest of the world. IP addresses are used to connect the whole networks together and form the internet. So they survive through the entire trip. Let's look at this ARP function. And this is one of the things that uses broadcasts. So the purpose of address resolution protocol is if I want to connect, I want to ping my server, and I don't know what his MAC address is. So I need to send out a broadcast message that says, calling all stations. If your IP address is 1.2.3.4, maybe that's the server's IP address. I would like for that server that has that IP address to respond to me and tell me what his 48-bit MAC address is. Because in order for me to send him the ping, I need to create an Ethernet frame with this actual destination MAC address in it. I don't know it yet. And the ARP function of the server will respond to that. He'll hear the broadcast. Everybody will hear the broadcast. Everybody will ignore it because they're not 1.2.3.4. Only the one single server whose actual IP address is 1.2.3.4 will hear that, and they will respond to that. So let's see some illustrations of this. Workstation H1 wants to send some information to H4 down here. He has his IP address, and he doesn't know his MAC address. He needs to ask for it. So what he's going to do is send out an ARP request in the form of a broadcast. Inside each workstation is an ARP table that is all these devices he's contacted, communicated with recently. What is the correlation between their layer 2 MAC address and their layer 3 IP address? And they hold on to it for about 3 minutes. If it's been more than 3 minutes and the workstation needs to resend to something, the ARP table will have timed out. He'll need to ask again. He'll need to perform an ARP request. It's a broadcast. Layer 2 Ethernet broadcast. So only the node that actually has that IP address, the 1.2.3.4, will reply. If he hears no request, then he won't be able to send the transmission. So this is a dynamic function. So here H1 is sending out an ARP request in the form of a broadcast. When broadcasts go on Ethernet switches, switches are compelled to flood it on all the other ports. All the other devices hear the broadcast, but only the one who actually has that IP address, 1.7, will respond. So he will send the answer back. So I'm the only one that has that address. Here's my MAC address. Mr. Workstation H1, please make a note of this and write it down and hold on to it for a couple of minutes. And you can start pinging me or logging into me and getting the file and print sharing, whatever you need from me. The other workstations, H2, H3, they say, I don't have that IP address. I ignore it. Now the original workstation H1 has the updated ARP cache, and now he can do what he wanted to do originally, which was send a ping or send a packet to that workstation H4. So that's the ARP process. And within devices in the same classroom, the 24 students would be able to learn each other's MAC addresses, finding what their IP addresses are if they need to ping them. What if you want to communicate out of the room or on the internet? Well, ARP addresses, MAC addresses, I can't communicate directly with these addresses. I'm not plugged in the same switch, but I am plugged into the same switch as my default gateway router, and he will find the pathway to communicate over the internet, the company network, or the global internet, and make that. So far as I'm concerned, that MAC address of my default gateway is the MAC address of the entire universe. So let's look at workstation A. First of all, he's going to send out a ARP request because he has nothing in his ARP cache here. It's empty. So he's looking for the MAC address located for workstation 10.10.10.3, which is host C. He's going to send out the Bradbury request. Everybody will hear it. All the other workstations in the classroom and the default gateway router for the classroom. Only one device actually has that IP address, and that's host C. So host C will respond. Nobody else responds. They ignore it. They drop it. Host C responds and updates the ARP cache. And now the ARP cache in host A is updated with the proper correlation between the IP address and the MAC address. And now you can do the ping or transmit the file or whatever you needed to do with that particular device. When you look at networking devices, The ARP table can look a little different than when you look on a desktop PC. It looks like this. You type the command ARP _A, and you get all the correlation between all of the IP addresses and MAC addresses that have been communicating on that workstation recently in the past 5 minutes. When you do it on a network device like a router or a switch, it's show IP ARP. I hope to be able to show this to you in Packet Tracer, and it will look something like this. Okay, now we're going to look at, I'm going to switch to a second PowerPoint presentation, and let's look at Ethernet switches function themselves. Hang this 1 second. I'll stop this. I'll start this. There we go. Okay, theory and operation of Ethernet switches. So Ethernet switches we put somewhere in the center of the building where we can plug all the PCs together. And Ethernet switches have a technology that, unlike the old hubs, which had lots of collisions, Ethernet switches have memory in them, and they have a processor, and they can just save up information, and there's no collisions. So long as each PC is plugged into its own private switch port, micro-segmentation to the desktop, there'll never be any collisions. So this is what's universally used today. It gives much better performance. So these are physical Ethernet switches that are actually doing this. So the switches in our that we have somewhere. Oops, I can't draw. Can I draw? Okay. The switches we have in our lab look like these. They're Cisco 2960 switches. They have 24 fast Ethernet ports, and they have 2 gigabit Ethernet ports, which can either be RJ45, or you can plug in a transceiver and use fiber optic cable. Not both at the same time. Fiber or cable, fiber or copper, twisted copper, your choice of one per port on those 2 ports. So they used to be called bridges. In the old days when Ethernet, the Cisco's first product was a bridge. That San Francisco Golden Gate looking logo that Cisco has came from that, the first product being a bridge. But the electronics have gotten much faster over the years. So in about the mid-1990s, all the old 24 and 48 port hubs started being replaced with 24 and 48 port switches. And we didn't have to do any software changes. And everyone's performance suddenly got much better. So today we call them switches, and sometimes I'll say bridge. Later on we'll talk about another course about the root bridge or the root switch. I blame the marketing guys. So switches operate at layer 2. They learn and store MAC addresses. We used to call them learning bridges. They set up a virtual private connection between 2 host machines that are trying to talk to each other. And so everybody doesn't hear all this traffic like the old hubs would do. But since they have buffer memory and real smart electronics in them, there's going to be no collisions. Just as long as you don't introduce any hubs into the equation, there will be no collisions. Here we have an Ethernet switch with several devices that are communicating with each other. These set up virtual private communications between all these different devices. And these devices only hear their own traffic. They don't hear the other traffic between the other host machines, sometimes called microsegments. So the circuitry, the sophisticated circuitry, and the switch does all this. So switches have much better performance than the old hubs did. I have dedicated bandwidth to each port, full duplex operation, which means I can send and receive at the same time, and no collisions. We should have no collisions if we don't put any hubs in here. In this case, we have a 26-port switch. We could hook 24 employee PCs and 2 servers to this switch, and there would never be any collisions experienced by any of these. So every host machine gets full dedicated bandwidth. 100 megabit fast Ethernet or gigabit Ethernet or 10 gigabit Ethernet speeds. He gets the full speed. With the old hubs, we had to share that amongst all the clients. Now, half duplex operation is like a CB radio. If I hold down the button of a CB radio microphone and talk, I can't hear you until I let go of the mic button. That's half duplex. A telephone is full duplex. I can talk on the telephone and you can interrupt me or you can say something to me while I'm talking and I can still hear you. So Full duplex is what Ethernet switches do. That means we can send and receive at the same time, and there's not going to be any collisions, like the old half duplex hubs were. So it's possible to set these settings on, let's say I'm plugging a new Cisco Catalyst switch into an old hub, and I want to make sure it goes down to half duplex. I can go to the command prompt and I can say full duplex, half duplex. Auto is on by default, and auto negotiation has gotten much better over the past 20 years. Normally, auto will work just fine, and it will automatically detect if he's talking to a half duplex connection or full duplex connection. Keep in mind that only standard 10 megabit and 100 megabit fast Ethernet are capable of half duplex. Gigabit Ethernet above is by definition full duplex only. It cannot go half duplex. So let's use collision-free switches, and everybody can transmit all at the same time, and no one will ever have any collisions. And any bottlenecks will be taken care of by the buffer memory that's present in the Ethernet switches, in case 20 people try to log into one server at the same time. Auto-MDIX is a feature where we used to might require a crossover cable between two locked devices, like two routers or two switches or two host machines. We would have to use a crossover cable. Most of the electronics in the past 10 to 15 years in particular have put in Auto-MDIX, which means that it doesn't matter whether you use a crossover or a straight cable, it's going to work either way. If it should have been crossover and used a straight, or should have been a straight, use a crossover, and it wouldn't have worked 20 years ago, it will work now. So for example, in 1995, when I got my first cable modem service, they had to use a crossover cable to connect my computer to the cable modem. Because otherwise it would have required, it required a crossover cable. If I used a straight through cable, it would not have worked back then, because Auto-MDIX was not yet around then. So let's take two switches and connect them with a straight through cable. Now, if it was our old 2950 switches that we had 15 years ago here, there would be no connection. Auto-MDIX is enabled by default, so I could plug a straight through cable between two switches and it would go and connect. If it was the old 2950 switches, I would have had to use a crossover cable because it couldn't work. And there's no Auto-MDIX built into the old 2950 switches. They're too old. And so generally speaking, when you plug two Ethernet devices together, you're going to go through a negotiation process to figure out what's the fastest possible speed we can both talk at, and are we half duplex, are we full duplex, and are we crossover cable or straight through cable? It'll automatically do all those things for you. Now let's look at the content addressable memory CAM table, or the MAC address table, and see how switches forward frames. So switches are separate broadcast domains in that, I'm sorry, they're separate collision domains. They do not separate broadcast. They don't separate broadcast domains. So if we had this is the old hub, these devices could all collide with each other. But the port they're plugged to on the switch means all the collisions will only be heard on this floor of the building. So we have 4 separate collision domains here. And nobody from the first floor can collide with people on the second floor. However, they will hear each other's broadcasts, because Ethernet switches by default forward. They flood all frames out, because what if you're doing an ARP request from this guy to this guy? They need to be able to hear each other's broadcasts for that to work. So switches forward broadcasts. Now, in the MAC address table, when you plug a device, in this case we have a device plugged into port 1, and he has this MAC address, and this is an abbreviated MAC address that's shown here. It's all actually a 48, 12 hexadecimal digits. So switches use this ARP process to bind MAC addresses with, switches bind MAC addresses to switch ports, listen to the source address, and they add that to their MAC address table. So when the response comes back, they know only to send it out port 1 and not to flood it out all the other ports. So the MAC address table and the switch is used to make this forwarding decision. And a router, the routing table is used to make forwarding decisions. We're looking at Ethernet right now. So in this case, we have 4 different PCs that have been plugged into ports 1, 3, 6, and 9. And right now in the MAC address table, there is only the entry for the one that's plugged into port 1, because he just transmitted something into the switch, and the switch learned it. So since the destination address is not known at this point, this is a unicast frame that workstation 1 sent out, but it has to be sent just like a broadcast out to all the ports. Has to be flooded because there's no destination entry. He doesn't have the 3333 in there yet. Now once he floods it out to all the machines, station 3333 will respond, and when he transmits back, his address will be added to the MAC address table, and now the two will have a private circuit and they won't have to do any flooding anymore. So switches are compelled to flood two things: all broadcasts, and what's called as an unknown unicast. Ethernet frame flows into the switch and the destination MAC address has not yet been learned. Once he learns it, he'll stop flooding it. So what happens when two devices send to the same destination? Well, if it was a hub, there'd be collisions. But in this instance, there's a separate collision domain for each port, so there will be no collision. And the buffer memory in the switch will accept both frames and send them one by one, and no collisions will occur. So if 10 people are trying to log into the workgroup server in the morning and put in their passwords, there won't be any collisions. The server will experience no collisions. So if it were a hub, we would have collisions, but if not, switch memory buffers frames and sends them out one at a time to the destination machine. And the sending PCs have no idea that they're both trying to communicate with the same device. They each think they have their own private communication. Okay, only one device on the switch port. There's no collisions. The only collision domain is between the PC and the switch. And since it's full duplex, no collisions. So if I use a full duplex PC and a switch port, there will never be any collisions. And that's what we've done for the past 15 years. Everything is full duplex. Now, how long are addresses kept in the source address table? About 5 minutes. How does the computer know the destination MAC address? Well, he does ARP requests and gets back ARP replies, and he updates his ARP table. We saw that earlier on the Windows screen. How many addresses can an Ethernet switch put in this table? Maybe 1,000. Well, there's only 12 ports, but a port could go to a hub with 24 devices in it, so they usually have large memory. What about layer 2 broadcasts? If a frame with a destination, a broadcast frame by definition is the destination address is all ones, all Fs, should be flooded to everybody. So it's an ARP request or a DHCP request normally. So it's flooded out all the ports so that has a better chance of someone hearing it, they can respond to it. And there's no transparent you have to worry about. So for every frame that enters the switch, two things happen. The first is the switch learns the source MAC address and puts it in the MAC address table. If it's already in the MAC address table, he resets the timer for another 5 minutes. If it's not in the MAC address table, he puts it in there for 5 minutes. By studying the source address of the frame that entered the switch. The second thing that switches do is once they have learned and updated the MAC address table, they look at the destination MAC address and says, let me look at my MAC address table and see what port number this guy's plugged into. If it's in the table, I'll only send it out that port. If it's not in the table, I have to flood it to everybody. Eventually, I'll learn it, and I'll be able to update my MAC address table. So in this case, the switch has got 8 host machines plugged into it, and the MAC address table has been updated with all 8 MAC addresses for all these individual machines. Okay, let's look at a switch, and we have just rebooted the switch so he doesn't have any entries in the MAC address table. I type the command, show MAC address table, and I get a big nothing. Actually, in a real switch, you're going to get a bunch of static entries, but the dynamic entries at the bottom, they'll be empty. So PCA will ping PCB. So PCA pings the ping address. Normally in the real world, the first reply would fail because of the ARP process. And now what's going to happen when we look at our MAC address table? He has learned the 2 devices plugged into port 1 and 2 that pinged each other. He's learned their MAC addresses. And they're in the MAC address table. They'll be there for if the guys stop right now, they'll be there for 5 minutes. If they keep sending data, After they completely stop sending data, he'll wait about 5 minutes, and then he'll erase them. Because it could be a laptop, and you could pick up your laptop and run from the classroom to the library in less than 5 minutes, so they have to fade it out after a certain amount of time. Now, PCC will ping PCD. What do you think is going to be in the MAC address table after those two guys? Now, they did this quite quickly after PCA did PCB. It wasn't no 5 minutes. So now when we look at the MAC address table, all 4 of these host machines are in the MAC address table. So now you can see that you can be a spy and you can look at your company's MAC address table on the router iOS, on the switch iOS, and you can figure out what's the IP address. I mean, what's the MAC address of all those machines plugged into each port? You can track down machines because that's a physical 48-bit burned-in value. That's a unique identifier of the hardware of that machine. And network managers do actually use this technique to do inventory. Now, what if I don't want anything in the MAC address table? I don't want to wait 5 minutes. I can type the command clear MAC address table and it'll wipe it. Now, switches record multiple entries for a single switch port. What if the MAC address table, what another switch is connected to this? In other words, the question is, why does switch 1 have multiple MAC addresses assigned to port 1 and port 2? Well, port 1 and port 2, this port's going to a hub which has multiple devices attached to it. This port's going to a switch which has multiple devices attached to it, and he needs to know how to get to all of them so he can have multiple entries. Let's look at the technique now of how the switches forward information. They establish a logical connection, a virtual circuit, only for enough time for the frame. And there's 2 methods of doing this. The default is called store and forward, which means I'm going to read an entire frame, and then after I receive the entire frame and make sure it's good, remember the CRC, make sure it's good, I will then make my forwarding decision and forward it. However, you're allowed to go in and reprogram and reconfigure the Cisco switch if you want to increase the performance. You can use fast forward or fragment free, and let's see what those mean. In store and forward, I'm going to read the entire Ethernet frame in and perform the frame check sequence, and then look in the MAC address table and forward the frame. Most latency. However, no errors in this gate because any errors will be filtered. Any error caused by the frame check sequence not being right, the frame will be dropped and he won't forward it. Now, the most liberal or the most aggressive method is cut through. I'm going to wait until I get the destination address. You know, that's the first thing that is in the Ethernet frame. And that's the only thing the switch needs to know to make his forwarding decision is the destination address. He's looking at the MAC address table. He's going to find the destination address. He can go and start forwarding that frame out right now, even before the rest of the frame comes in. The danger is there's no error checking. But the good thing is the lowest latency, the most fastest possible speed. So if you want to brag about high performance, you're going to program for that. Now, it turns out that if there are going to be any errors in Ethernet, it almost always occurs within the first 64 bytes or so. So as a man in the middle type of a thing, as a happy, a centrist, if I wait 64 byte lengths and then cut through, it's not super lowest latency, it's fairly low latency, but it catches most collisions and filters most errors. So that's a sort of a man in the middle effect you could use if you wanted to do that. Out of the box though, they're store and forward. So in store and forward switching, I'm going to read in the entire darn frame and don't forward it until the entire frame is read in. So if there's any errors whatsoever, this is going to catch it because the CRCs won't match. Or it could be a collision run, a collision fragment, or so, excuse me, also if we're doing any quality of service, like for example, it's a voice over IP telephones and needs to go to the head of the line, we can read the entire frame and we can do that quality of service processing. So once the entire frame has been read, he will forward it. And this is the only method we can use if there are different bandwidths. So let's say your employee PC is attached to the LAN at 1 gigabit, but the server is attached, workgroup server is attached at 10 gigabit. Well, since there are different bandwidths, we would have to read the entire gigabit speed from my desktop PC into the memory chip, the buffer chip, and then shoot it out at 10 gigabits. And when the server sent its answer back, it would shoot into the switch at 10 gigabits, and then it would dribble out to me at 1 gigabit. So when you're different bandwidths, you have to do store and forward. Cut through fast forward is, let's just wait till the end of the destination MAC address. This is very, very fast, very low latency. If any errors occur, though, it's not going to catch them, and we're going to carefully forward garbage onto the network. However, the two ports must be the exact same bandwidth. So it can't be like between a server and a client. So fragment-free is our centrist view. Now we'll wait about 64 byte lengths. And if any errors have occurred, they probably would have occurred by now. Most of them, 99% of them would have occurred by now. So I can at least get lower latency, a little bit faster processing time, and don't forward so much garbage onto the network. But again, the two ports must be the exact same bandwidth or speed. Now, what about this buffering memory that's present in the switch? There can be separate memory buffer chips for each individual port-based memory buffering. Or there can be shared memory buffering where a big bank of memory is split up among several banks of ports. And depending on the manufacturer and the model, they can engineer this which way they want to. So in port-based buffering, each incoming port has its own memory chip, its own buffer chip. If maybe it's the one connected to the server and 10 people are trying to log into the server at the same time, it's 9 o'clock in the morning. So the buffer memory saves up the first, they saves the 9 of these login requests will be held in memory, and the first one is sent live to the server and he logs it in, and then the second one is sent, and then the third one is sent. So this can this make sure no collisions occur and fast servers can talk to slow employee host machines. The limitation is each port has a fixed and limited amount of memory. In shared memory buffering, we're going to take a larger amount of memory and share it among maybe 8 ports or 16 ports or 24 ports. So if one port is really, really, really busy, like the gigabit Ethernet port to the server, you can use more of that shared memory pool. And all those ports that aren't being used right now, they won't use any of it. So if we're doing asymmetric switching between a 1 gigabit client and a 10 gigabit server, we have to use shared memory buffers for that to work. Now let's look at some enterprise level switches, and then I'll do a little packet tracer stuff here. So our switches that we have are fixed configuration switches, like 2960 switches. They cost about $500 a piece for a 24 port model. If you wanted a 48 port model, it'd be more like $1,000 a piece. They're fixed because I can't add any more ports to them. We're stuck with whatever features came with the switch when it was manufactured. Modular switches, and the next time you come in the lab, look in the back of that room on that rack, and that server rack that's in the back where the printer is. There's a modular configuration model 4000 Cisco switch that you can plug in a circuit board and add more Ethernet ports if you wanted to. These are more expensive. The one that we have there was a $20,000 switch. So we can customize it to what we need for our particular company. I need these many Ethernet ports, and they're a twisted pair. I need this many fiber optic connections between the buildings. So fixed configuration switch is the lowest cost. Modular switches are the highest cost. In the middle are called stackable switches. We can take switches and put up to 9 switches in one rack and tie them together with these silver umbilical cables. And it turns a rack of 9 Cisco switches with 48 ports into roughly a 450 port switch with one IP address to manage it. So that's commonly used at the access layer to connect to employee PCs. You would never want to use this in a server center. Doesn't have the performance for it. So enterprise switches can have, these big switches that cost $1 million can have 4,000 ports. And they have very high performance. Instead of connecting the switches together with Ethernet cables, we have a very fast backplane, processing plane in the back of the box. So port density can be very high. And very high forwarding rates. They can forward data from one port to another port on the same switch at much higher rates than standard Ethernet. And link aggregation is a term for if I want to run one fiber optic cable to the library, I'll only get 10 gig. And what if someone chops up that fiber? Well, if I run 2 fiber optic cables to the library, I can aggregate or link those ports together. Cisco calls it Ether channel. And I could get 20 gig. If I could have up to 8 fiber optic cables between the library and our business building, and get 8 times 10 or 80 gigabits of traffic. And if any one of these lines got dug up, I would still get the remaining capacity of the others. Okay, it looks like our last topic is power over Ethernet, and that is a feature that in a wired Ethernet cable, that, say for example, RJ45 with 8 wires in it, and it goes to the desk in the front of the classroom, and there's a Cisco phone there. And the Cisco phone requires a little bit of power, about as much as a Christmas tree light, not a lot. So we can use the same cable that goes to the switch to send both the data connection for the sending and receiving of the telephone calls, as well as the electricity to power up the phone and make it ring and light up the LCD display, if the switch is power over Ethernet capable. This adds a small cost to the switch itself, just a few dollars to each port. So all our Ethernet switches that are in our Tarrant County College production network have this because we have lots of power over Ethernet. We have lots of power over Ethernet powered Cisco phones. We also have Wi-Fi access points. And that way we don't have to run a circuit up into the ceiling for 110 volts for the plug in the wall wire power supply. We can power that Wi-Fi access point off that one cable, and the cable will carry both the data to the Wi-Fi access point, as well as the power to make the electricity to make it work. Very small amount of electricity, as much as the battery would give us. Another device that typically is very convenient for power over Ethernet is IP surveillance cameras. So you can put one at the top of a warehouse and you only have to run the data cable up there. You don't have to run power to it. Now, let me hang loose a second and stop this. And I'm going to see if I can show us this feature about how the MAC address table works in Packet Tracer. So let me see, I can share now. Okay, if I do this, and I go this, and I want to share this screen. I want to share the entire screen for Packet Tracer. Is it being shared? Okay, and now I'm running this on a Macintosh, and I had some bugs on this earlier, so we can see if we can get this to work now. So in the lab, what you're going to do is you're going to go and get a hold of a, oh, I'm clicking on the wrong place, sorry. So we're going to click on switches and pull the switch into the topology. And then I'm going to click on a host machine and bring a host machine in the topology. And we'll connect these together with a standard Ethernet cable. So I'll connect Ethernet port to port 6. And let's go ahead and apply some IP addresses to this. So I'm going to pull up my lab report so I can use something that's similar to this. Okay, I'm going to go into the switch configuration panel and just give them a basic IP address. Click on the fast Ethernet port. And in the lab, the VC is going to be 192.168.1.3. Mackley fills in the proper subnet mask. And then let's see, we're going to close that, and we're going to go to the switch and put a basic configuration on the switch. Let's see if this works. It was giving me some trouble earlier. Okay, so everybody should be able to see the switch console port. So I'll go to the privilege exec mode and go to the configuration mode and give them a host name of switch 1. And then I'm going to go to the interface VLAN 1 and give them an IP address so we can ping and create some traffic. I'm going to give them an IP address of, let's see, he's given 192.168.1.2, 255.255.255.0, and then we'll do the no shutdown command. And then let's see, now I should be able to ping the host machine 192.168. Ping back. Why did that first ping fail? We got the dot, and then we got the 4 exclamations. Exclamation mark is successful, dot is failure. The ARP process was taking place in the background. The address resolution protocol broadcast was sent out, and the host machine responded, and that usually causes the first ping or two to fail. Now, Let's go look and show if we can see the ARP table. Ah, looky here, we see the two IP addresses involved, the one from the switch, 1.2, and the one from the PC, 1.3, and we see their MAC addresses. Now there's the part that was giving me trouble before. Let me see if I can show the MAC address table. It's working today. Okay, good. So this PC is plugged into port number 6, and here we see his MAC address. So he has successfully updated the MAC address table, and that's working properly. And that's basically pretty much all there is to this lab here. They asked you some questions about, let me just go through the lab here and see. He's going to have you console it up and, you know, do the passwords and things of that nature, and then look at the PC and look at his IP address. So pretty straightforward lab. Okay, let's see now. So I talked about, let me go back to here. Some of you guys weren't here when we first started. Stop sharing this. Share the tab. So this very first link I have in the announcement section, please, I advise you, recommend that you click on this and go to the bottom and click this link to join, create a course for you on the Cisco Networking Academy to prepare for this bridge thing. It will be this Thursday. And then when Thursday comes, click on this link at the top of the document and join the Cisco. It's like Zoom. It's like our Cisco Collaborative, Cisco WebEx. It's a work group collaboration software. And this will give you some information about the jobs. This is a local thing here in the Dallas-Fort Worth area. Give you some idea of what it's going to be like once you get your CCNA certification and get out and join the technical workforce that we have here. That's this Thursday at 2 o'clock in the afternoon. And be a good thing to attend. And the other thing I mentioned was when you come back in the spring, you guys that are taking this course and you want to get your full CCNA course, this course, Introduction to Network course we're having right now, that will end just before Christmas. Do not take CCNA 2 in the spring. That's the old progression. Take CCNA 3 in the first 8 weeks and take CCNA 4 in the second 8 weeks. If you take it at my campus, it'll be on Tuesdays and Thursdays at 9 o'clock, and every Tuesday will be a lecture. And every 9 o'clock at Thursday will be the in-person lab if you want to come to the in-person lab. And CCNA 3 will be in the first 8 weeks, and then we'll have spring break, and then CCNA 4 will be in the last 8 weeks. And you'll be totally prepared then by the first week in May to go and take your CCNA examination and really put yourselves in a better position in the job marketplace we have in the Dallas-Fort Worth area, because we're pretty hot around here. Okay, I'm going to say let's go ahead and stop now, and I'll hang loose to see if anybody's got any chat thing they want to say, and then we'll call it a day, and this will be another one for the books.